Okay, thank you, Vikram, for that kind introduction. And also, I should thank Zoom that I can have an audience in Dublin and giving the lecture from India. Well, as you know, I'm not a mathematician, so don't expect much of mathematics in this lecture. If I can convey some of the magical aspect of Ramanujan's mathematics, that will be sufficient. Srinivasa Ramanujan is undoubtedly the most brilliant and the most famous mathematician India has produced in the modern era. He was born in 1887 and died very young in 1920. Not only such a short lifespan, he had to face other difficulties during his lifetime. Like for most of his life, he was very poor. He had financial constraint. Number two, he had health problems during his peak activity in Cambridge. And lastly, he didn't have any formal education in higher mathematics. Of course, some people say that was good for him, but he didn't have, because that's why he was so original. Though he ended up in rediscovering quite a few results, but even those are very novel approach. The best biography of Ramanujan is written by Professor Kanigal, The Man Who Knew Infinity, which you know has been also converted into a beautiful movie. Actually, Ramanujan, during his young age, was so poor that he couldn't even afford papers to do his mathematics. He used to do all his mathematics on a slate and only copied the final result in the notebook. So his thought process is lost, only the final results were available. One such notebook was rediscovered in 1976, that is more than 50 years after his death, in the Cambridge Library Archive. And there are about 900 new results and theorems in this notebook. If people are interested in knowing about Ramanujan's math, then these two mathematicians, I think, are the best Ramanujan scholars in the present day. Now, as I said, I'll emphasize only the magical aspect. So maybe the best point to start is a magic square. All of us know what is a magic square. This is a 3 by 3 magic square. And actually, 1 to 9 is written, as you know, and you add along any row, any column, or any principal diagonal, the sum total is the same, 15 in this case. There is a very simple algorithm to fill up all odd order magic square, 3 by 3, 5 by 5, or 7 by 7, whatever it is. So the algorithm is you write 1 in the center top square, then always try to go diagonally upward to the right. So 1, then I go here, but we have gone beyond the magic square by cutting across a boundary line. So the algorithm says then you go down to the extreme end along that column. So I write 2, then again I try to go right along the diagonal. I go out, cutting a boundary. So following the same rule, I come here, the opposite end, 3. Now the second rule, if I try to go up and it is already filled up, then just come down. 3, then 4, 5, 6. Now again you are going out, but cutting through a corner, not through any boundary line, but through this corner. Then if you go through a corner, then just come down. So you write 7 here, then 8, 9. Just to follow that is what's in every case, let me take a 5 by 5 square. 1, 2, 3, 4, 5. It is filled up, so come down. 6, 7, 8, going out, come down. 9, going out, go to the opposite end. It is filled up, so come down. 12, 13, 14, 15. Cutting across the boundary corner, so you just come down. 16, then go out. 17, 18, 19, 20. It is already filled up, so come down. 21, 22. Go to the other end, 23, 24, go to the other end, 25. Here, if you add, you will see it will be 65. Now, let us come to a even order magic square. One of the famous magic square of 4 by 4 was by German famous painter Albrecht Dürer. He was so proud of his 4 by 4 magic square, he knew that it might be lost unless he puts it in one of his great artwork. So what he did, Melancholia, this is an engraving which is famous, all over the world and lasting for more than 500 years now. Melancholia is this lady, winged lady under deep depression. And he included his magic square in this engraving so that it, lasts for centuries. Now, why is he so proud of this magic square? Because as you see, this is a normal magic square. If you add up along the column, diagonal, row, you get the same thing, 34. But also, if you add only the corner elements, 1, 13, 16, 4, then also you get the same 34. If you add up these 4 or these 4, which are colored the same way, again you get 34. If you again add up the same colors, you get the sum total as 34. The same thing here, 8, 2, 9, 15 add up to 34, 5, 3, 12, 14 add up to 34. Even if you add 8, 3, 9, 14, that is the movement of a knight in the chessboard. A knight moves from here to there, then there to there, then there to there, and there. Similarly, a knight starting from here can go there, then there, then there. You add up all, you will get 34. So, because of this special characteristics, he was so proud. Now, let us talk of Ramanujan's magic square, which had all the properties of the Dürer magic square, but he started not from 1 to 16. He used his date of birth, 22nd December 1887. And he filled up the other 4 numbers so that this magic square has all the properties of Dürer magic square except that ninth movement. But it had one more characteristic, that these 4 and these 4 also add up to 139 as any row or column or principal diagonal. This was the Dürer magic square. Here you see these 4 do not add up to 34. 38 here and 30 here. But here that ninth movement from 12 to 8 to 3 to 9 to 14, this is not true here. 25, 12, 10 and 23 do not add up to 139. Okay. So let us leave the magic square here. Not leave the magic square here. Ramanujan also gave in his notebook 1, how do you make a Ramanujan's magic square? What he said, write any 4 numbers, A, B, C, D. Obviously, it is a 4 by 4 magic square because all rows and all columns and the principal diagonal give you summation of A, B, C, D. And if you add another 4 by 4 magic square with different numbers, P, S, Q, R, and you make this 4 magic square, then you add up these 2, like A plus B, all the corresponding elements you add up. And then this 4 by 4 magic square will be Ramanujan's magic square. So he started with, 12, 22, 12, 18, 87. So if you take A, B, C, D, then you can find P, S, Q, R. So that 12, 22, 12, 18, 87 comes. A equal to 4, B equal to 5, C equal to 6, D equal to 7. If you take, then you can easily solve for P, S, Q, R because these are known. A plus B is known, D plus S is known, C plus Q is known, B plus R is known. So knowing A, B, C, D, I can find P, S, Q, R. So I can fill up these 4 magic square, then add up these to get Ramanujan's magic square. Now we come to a very special number which is known as Hardy-Ramanujan taxi cab number. There is a story behind this number. When Ramanujan was sick in England, he was admitted in a hospital in Putnam area in London, and Hardy came one day from Cambridge to visit him. And Hardy and Ramanujan were very good friends mathematically, but otherwise social talking, due to cultural and everything different, was not very warm. So Hardy didn't know how to start the dialogue with Ramanujan. So he said, Ramanujan, today I came by a taxi. I think the number is absolutely dull. There is nothing in it. Immediately, Ramanujan said, no, 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 Hadi, this is a very special number. This is the smallest number which can be expressed as sum of two cubes. Like 12 cube plus 1 cube is 1729, 10 cube plus 9 cube is 1729. There is no number below this which can be expressed in these two different ways of sum of two different cubes. So Hardy was obviously stunned, and he remembered why his friend Littlewood said all natural numbers were his personal friends. And now I'll show that really this particular number was his personal friend. It was nothing new to him. Just to tell you that taxi cab number, the whole thing became a number theory problem. Another Indian number theorist, Sarvadaman Chawla, he wrote to another Indian mathematician, S.S. Pillai, in 1929, 9 years after Ramanujan's death, that he thinks this number is the smallest integer that can be expressed as sum of two positive cubes in three different ways. Not two different ways, but three different ways. That is what he wrote to Pillai. But later on, it was found that that is not the smallest number, that is actually the fourth smallest number. The smallest number is this. There are two more numbers like this. As you see, this number can be expressed as sum of two cubes in three different ways. This cube plus this cube, 228 cube plus 423 cube, 255 cube plus 414. So now this is called taxicab number of order 3, and Hardy taxicab number is called taxicab number of order 2. It has been proved that taxicab number of all orders exist, but only up to T6 have been found so far, because the numbers are monstrous, as T4 is this number. Sum of two cubes in four different ways. This, 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 and this. And this is T5 and this is T6. Now let us see why 1729, the taxicab number of Ramanujan, was his close friend. To do that, let us start with this famous problem, which is now not a conjecture, it has been proved, that x to the power n plus y to the power n equal to z to the power n. This equation has no solution for integer values of x, y, z for n greater than 2. For n equal to 3, 4, it is not valid. It is only 2 for n equal to 2, which we call Pythagorean triplets. Euler had already proved it for n equal to 3, but general proof was not there. So Ramanujan said, okay, I know x cube plus y cube cannot be equal to z cube, but can I search for numbers x, y, z? So it is off by only one. X cube plus y cube equal to z cube plus 1, and x cube plus y cube equal to z cube minus 1. And then he found this. X cube plus y cube is z cube plus 1. X cube plus y cube is z cube minus 1. So this is the famous taxicab number. So Ramanujan found it much earlier. Not as the smallest number of 12 cube plus 1 cube, but it said, z cube plus 1 is x cube plus y cube. This triplet. Then he said how to generate more such combinations. So Ramanujan identities from his lost notebook. This is one page from his lost notebook. It is Ramanujan's handwriting, very nicely handwriting. He wrote this rational polynomial, and then he claims if these are true, and these are the coefficients of this, then an cube plus bn cube will be cn cube plus minus 1 to the power n. So if n is odd, this will be minus 1. If n is even, this will be plus 1. So he has got a set of numbers which satisfies an cube plus bn cube, if cn cube plus minus 1. And then he writes this 6th example. And you notice here that 9 cube plus 10 cube, 12 cube plus 1. Now, how did he write this? There is nothing left in the notebook. These are all gone with his slate, because this is from his lost notebook. It is only in 2004 one mathematician showed that xn, yn, zn can be, this to the power n plus minus 1, 2, 2. This matrix multiplication will generate this xn, yn, zn, which will satisfy this equation. For n greater than equal to 1, you get one set by taking plus 1 here, you get another set by taking minus 1 here. For example, with n equal to 1, that means no matrix multiplication needed, only one vector and matrix multiplication. With n equal to 1 and positive sign, this plus 1, you get 135, 138, and 172. I hope you remember that that was Ramanujan's three numbers. And with minus negative sign, with a negative sign, that is minus 1, you get 9, 10, and 12. This is not the only way. Ramanujan's notebook also contained the following formula, that if u and v are arbitrary integers, positive or negative, and we define four numbers a, b, c, d by u and v in this way. U and v can be any integers, positive or negative, and you define a, b, c, d like this in terms of u and v. Then he, very simple algebra shows that a cube plus b cube plus c cube equal to d cube. Whatever may be u and v. This Ramanujan shows. You can do it. It is just a few pages of school algebra. Only thing, if you have to remember that we know 3 square plus 4 square is 5 square, but we might not have noticed that 3 cube plus 4 cube plus 5 cube equal to 6 cube. That will be needed to prove this. That 3 cube plus 4 cube plus 5 cube is 6 cube, which are they all appearing 3, 4, 5, 6. So if you put u equal to 1 and v equal to minus 2, we get a equal to minus 27, b equal to 30, c equal to 3, and d equal to 30. So if you put this ABCD here, you get this, which means you keep these two terms here, you take this term on the other side, and take 3 cube out, then you get 1 cube plus 12 cube, 9 cube plus 10 cube. So again, Ramanujan had this so-called taxicam number. So what I wanted to mean that 1729 appeared as magic to Hardy because this lost notebook was not there. Okay, there are lots of formulas for approximation of this universal mathematical constant pi. So, which we know as Gregorian-Leibniz series. This is the simplest series, very simple, just alternate sign and reciprocals of odd numbers. This series was so simple that even Newton appreciated Leibniz, which is not a very, Leibniz was, Leibniz and Newton were not very friendly. But this was in 1671 and 1673. But Indian mathematician Madhava gave this series in the 14th century. That is 300 years before them. But this series is no good for calculation of pi because 500 terms are needed for accuracy of 3 decimal places. This series is very slowly converging. So there are lots of series. Ramanujan, for example, rediscovered, which is known as Bauer series, which is better. But in 1910, Ramanujan really took the world by storm. In India, in magazine, he published this, Indian Journal of Mathematics. This is the formula for 1 by pi is this. And here, just k equal to 0 if you take, you get the pi value 6 decimal place accurate. And if you take one more term, every additional term adds 9 more decimal places of accuracy. So this was absolutely magical formula for Ramanujan. In fact, a little variation of this done by 2 Russian brothers is one of the fastest algorithms for computing this universal constant pi. And it has been used to calculate more than 1 trillion decimal places. This is the Russian brothers formula. You see, very similar to Ramanujan, only these numbers are different. But in form, it is very similar. Another famous approximation of Ramanujan is this, pi by 4 in 97, 9 by 22, which gives you 8 decimal place accurate results for pi. This he got from, of course, a continued fraction. He was a master of continued fraction and infinite radicals. So pi by 4 is 97 by plus 1 by 2 plus 1 by 2. And here you see, if you neglect this 16539, if you truncate the series here, after 1, you don't write 1 by 16539. That is the inaccuracy. Also, 8 decimal place accurate. Ramanujan even, this is another famous approximation of pi, which is 6 decimal place accurate. This was given by a Chinese mathematician long, long ago, not in the modern era. So Ramanujan made a geometric construction for 355 by 113. This is the page from Ramanujan's notebook. If we draw it like this, it started from a unit circle, then simple construction which any school student can do, just dividing half, half, two-third, one-third, and then drawing parallel lines and all that kind of thing. You get RD square, this R to D. This RD square comes out at 355 by 113. So if we get RD square, we can always get RD. Okay. Square rooting is easily done geometrically. Ramanujan also provided a geometric construction for his 97 by 4, the 97 4 by 22. Here is the SO. So these details I don't expect you to remember or understand here. And I think we've talked enough and I can take a commercial break now. So all the geometric construction is available in this book. And because the book is written by me and I'm advertising my own book, so I can call it a commercial break. This famous number is called Ramanujan's constant. Actually, Ramanujan found lot such numbers. You see, this is an E transcendental number, pi a transcendental number, square root of 163 an irrational number. But Ramanujan claimed that this number is very near, very close to an integer. In fact, when with computer it has been calculated after 18 digits decimal place followed by 12 nines. So you can easily say it is 744. In fact, Martin Gardner made an April Fool joke in his magazine that, Scientific American, regarding this number. In 1911, Ramanujan posed the following problem for the readers of Indian Mathematical Journal. He gave this right-hand side and asked, what is the left-hand side? Nobody could answer it, and he gave the answer after 3 months, that the answer is 3. So how did he do this infinite radical to get 3? Maybe the other way around is easy. If you give me 3, I can write the right-hand side. Because if you 3, I can write square root of 9, then 1 plus 8, 1 plus 2 into 4, 2 into square root of 16. 16 is 1 plus 3 into 5, 3 into square root of 25, 1 plus 24. So you see, 3 is that infinite radical is coming. And if you calculate approximation with various terms, you get first 1, then square root of 3, then square root of 5, blah, 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 and tends to 3, as you see. Because 3 is 1 plus 8 square root, 2 root 16. So I can write if n equal to 2, and this is n plus 2 whole squared. Then for any general n, I can do this n squared plus 4n plus 4. Then I can write 1 plus this, and this I can factor n plus 3 into n plus 1. So you see 1 plus n, square root of 1 plus n, and this n plus 3, I write square root of n plus 3 whole square. So if it is true for 2, it will be 2. You can go to 3. If it is true for 3, it will go to 4, like that. But how Ramanujan obtained this? This is, I have gone from the right-hand side, left-hand side to the right-hand side. But how Ramanujan came from right-hand side to left-hand side? That he gave an identity that this is true for all values of x, this infinite radical. And if you put x equal to 2, you get that previous expression. 3 equal to 1 plus 2 into 1 plus 3, 1 is 2 plus this is 4, this is 3, this is 2. So you get that expression. But the question is, how did you get this? How does one get the above identity? He got it from a more general form, also given by him, that he gave this infinite radical. If function of x is x plus n plus a, which is defined by this, now how you see this equal to this? I think only Ramanujan can see it through his magical eyes. But if he says it is true, let us believe and try to see that, verify this, not prove, just verify. I have underlined the word verify. Square both sides to write fx squared is ax plus n plus a whole square. Plus this is nothing but x into fx plus n. All x's has been replaced by x plus n. So now you can take this term to the left hand side. Then a square minus b square, you can write a minus b into a plus b. And here you have this. So if first term is equated to x, then second term is automatically satisfied, right? If fx is minus n plus a is x, that is fx equal to x plus n plus a, as Ramanujan wrote, and the second term is automatically valid. Now you put a equal to 0 and n equal to 1 in this identity to get this. So this infinite radicals he could dream of. Now he gave a lot of arithmetic function like mock theta function and all that. That is too high level mathematics for me. I will talk of a funny function which all of us can understand. That yx is 4 minus 3x, 16, 9x squared, 24x x cubed. Then whole thing to the power 1/3. And this is minus and whole thing to the power 1/3. And the x goes from 0 to 1. Now, what is the value of y at x equal to 0? You put x equal to 0, this is 25, this is 25, so this term vanishes. 4 minus, sorry, what did I say? 25, x equal to 0. So this is 4 here, this is 0. So this is square root of 4, this is 0. So square for 4, so this is 8 to the power 1/3, which is 2, and this will be at x equal to 0, y is again 2. And x equal to 1 again, y equal to 2. The mysterious aspect is that you put any value of x between 0 and 1, it will be 2. That is not so easily seen. Only he could see. But once he gives this, we can easily prove it because we cube it to y cube equals to 8 minus 6x, and this 3ab into a plus b is y, and and this is gives you this. Y cube equal to 8 minus 6x into 3y and x. So 8 you take it to the other side, y cube minus 8 minus 3x into y minus 2. So you get this. So one root is y equal to 2, and that is the only real root. The quadratic equation here, so long x between 0 and 1, will give you complex roots. So funny function has been verified again, not that how he could write it. But later on, a plus bx, if you write, you can easily generalize it by writing a plus bx. Now we come to a story. In December 1914, Ramanujan was asked by his friend P.C. Mohalanavis to solve the following puzzle that appeared in the popular English magazine Stand. Every Sunday they used to give a maths puzzle. So Ramanujan solved it, and the problem goes as follows. There are n houses on the side of a street which are numbered sequentially starting from 1. The sum of the house numbers on the left of a particular house having the number m equals that of the houses lying on the right. It is given that n lies between 50 and 500, determine the value of m and n. This was asked by Mahalanobis. That was the puzzle Mahalanobis solved, and he asked Ramanujan. Just to explain the puzzle a little more clearly, what I'm saying, there are n number of houses numbered 1, 2, 3 like that, and there is a particular house m such that if you add 1 to m minus 1, and if you add from m plus 1 to n, they become same. Then what is the value of m? And obviously then you get the value of n. And it is given n is between 50 and 500. So as Kanigal describes, that Ramanujan, while starting his vegetables on the gas fire, rattled out a continued fraction generating all the values of m without any restriction on the value of n. So Mahalanobis obviously was stunned, and when he asked how he had solved the problem, Ramanujan answered, immediately he heard the problem, it was clear that the solution should obviously be a continuous fraction. It was obvious only, I think, to Ramanujan. And I then thought, which continued fraction? And the answer came to my mind. This is obviously, again, a magic of the highest order. Now let us put it mathematically. What is it? 1 to m minus 1 and m plus 1 to n. These sums are equal. So if you do a little bit of algebra, AP series, you can add and you get this. So you have to solve this equation for integer values of m and n. As you know, during Greek mathematics, these are called square numbers and these are called triangular numbers because there everything was geometry, and this geometric shape, triangular shape, equal to 3, 6, 10. These are, which is n into n plus 1 by 2 with n equal to 1, 2, 3, you get this. And this m square is just, these are called square numbers. So long before Ramanujan in 1733, Euler answered for what values of n the triangular numbers also are square numbers, which means triangular numbers are also square numbers for what value of n. This was answered by Euler in 1733, and he gave these answers. With n equal to 1, 849, 288, 169, and 0 are square numbers corresponding to m equal to 1, 6, 35, 204, and all. Because n was between 50 and 500, so this was the answer for Mohanadovicius of Stand magazine's puzzle. N is 288 and m is 204. So the normal way of solving such equations, if I write this, take 2 and then multiply by 4 and add 1 to get this. And put p equal to 2n plus 1, so it is p square, and q equal to 2m, so it is 2q square. So I get p square minus 2q square equal to 1. So if I can solve p and q, then I can get n and m using this. So p square minus 2q square equal to 1, so I can write p minus root 2q into p plus root 2q equal to 1. So by just trial and error observation, I can get one small solution very easily. P equal to 3 and q equal to 2. Where 3 square is 9, q square is 4 into 2, 8. So this equation is satisfied with p equal to 3 and q equal to 2. Where this is, and when n equal to 1 and m equal to 1, which means there is only one house, some of the houses on my left and some on the numbers, add some on the right is also 0, both are 0. Now, once I get this smallest solution, then we can get all infinite solutions just by squaring. You see, 17 and 12 will be the next values of p and q. When n2 will be 8, m2 will be 6. So if there are 8 houses and m is the 6, that means 1 to 5 is 15, 8 plus 7 is 15. So this is the second solution. Combining both sides of equation, cubing this, you get this. So you get the third solution. So this process can continue. Actually, these equations because Euler said Pell's equation, everybody now in our textbook, everywhere, it is called Pell's equation. But much before Pell, even European mathematician Fermat discussed this kind of Diophantine type equation. The integer values of P and Q find, but D is a non-square positive integer. Because if D is a square, then dq square also will be a square. So two consecutive square differ by 1, the trivial solution 1 and 0. So D is a non-square positive integer. But this format was in 1601 to 1665. But Brahmagupta, in his Brahma Bhuta Siddhanta, about 650 AD, they put 1000 years before Fermat, gave this equation. P square minus 92 Q square equal to 1. He challenged, those days mathematicians didn't have a profession as a professor. They could challenge other mathematicians so that king only listens to him, that he is the best mathematician. So he challenged all other mathematicians that if you can give me the solution for P and Q within 1 year, I will accept you as a great mathematician. Because he knew the smallest solution in this case is P1 equal to 1151 and Q1 equal to, probably, I cannot read it, 120 something. So he knew nobody can get it by trial error like 3 and 2. Actually, this equation, Brahmagupta's equation, is notorious because a little change in D can cause drastic changes in the values of P and Q. For example, B equal to 60, P1 equal to 31, the smallest solution, Q1 4. And 61, this. 62, again, very small. And if it is this, then astronomical large numbers. Ramanujan's solution, how did he get it? He got the first two values of m, namely 1 and 6, with n equal to 1 and 8 respectively, mentally. Immediately obtained the continued fraction using only 1 and 6. This continued fraction. And this is the continued fraction he rattled to Malanovic. He said you truncate at any stage, you get two m values, two values of m. 1 by 6, 6 and 35, 35 and 204, and so on. And that was the answer Mohananavish was looking for, because 204 n will come out as 288. But how could he see this continued fraction, just from two values 1 and 6? Ramanujan's continued fraction is this. So if I take is the converging thing, so I can write this also as x. So x is 1 by 6 minus x. So this gives me a quadratic equation where I can solve is, since x is less than 1, x equal to minus 3 root 2, and 1 by x is 3 plus 2 root 2. So I get that primitive solution. So Ramanujan's continued fraction gave me the primitive solution. And obviously, he could see it. This, so many layers of mathematics through him. Now, let me take another commercial break, I think, because all that I've discussed from the first commercial break and this commercial break, these are available in this book, again written by me. So I say it's the commercial break. Let us now go into Hardy as mentor. That is a very fruitful period in Ramanujan's life. He became famous only because Hardy took him to Cambridge. But in Cambridge, Ramanujan wanted to be a graduate. The Hardy was very, Hardy was not happy. He said, no, you should create mathematics. Degree is not good for you. Ramanujan said, but in that case, I'll not get a job when I go back to India. So I must get a graduation degree. So Hardy arranged everything. The course requirement was waived, as Ramanujan preferred to sit alone in his room. So no examination. He submitted a 52-page printed 52-page paper on highly composite numbers. This paper is so long that this paper itself has a content pages. It's a very long paper on highly composite numbers. And this is the graduation ceremony, graduation. This is the shortest person here is Ramanujan. A highly composite number is characterized by having more number of divisors than any composite less than it has. So the first composite number is 4. 4 has 3 divisors, 1, 2, and 4. But 6 has 4 divisors, 1, 2, 3, and 6. The next is 12, 24, 36. The list goes on, and Ramanujan listed all such numbers up to 6 trillion, almost 7 trillions. And it was found later on that he overlooked only one number. This number Ramanujan missed. Computer has calculated it, but Ramanujan missed it. So why did he calculate these composite numbers to such a high value? Because he also gave a very nice asymptotic formula, and he wanted to test the accuracy of his asymptote formula as that how many composite numbers are there, highly composite numbers are there up to a given integer n. He found an impressive asymptotic formula, and to test that formula, he created those. We know any composite number can be written in terms of prime factorization, but highly composite number has a property, according to Ramanujan, that for highly composite number, a greater than equal to b greater than equal to c greater than like this, and this last fraction will be 1. Last, of course, it goes higher up prime number, then the last index will be 1. As you can test here, 2 is greater than 1, 3 is greater than 1, 6 greater than 3, greater than 2, greater than 1, like that, and the last is 1. But there is one exception for 36. 36 is 2 square into 3 square. So last power is 2, not 1. That is the only exception in this entire list of highly composite numbers. But happy collaboration between Hardy and Ramanujan continued, and their most famous work is on partitioning of a number. You see, partitioning means an integer, how can it be written in different ways using smaller integers, including that itself. So partition of 4, as you see, is 5. 5 different ways you can write 5. And this number of partitions increases very rapidly. For example, partition of 10 is 42, partition of 15 is this. So Ramanujan wanted to have a formula for Pn for any arbitrary n. What is the number of partitions for any arbitrary number n? And here in this work, Ramanujan's creativity and Hardy's technical skill had a fantastic collaboration. So they finally got Pn to be given by the nearest integer to a series to be calculated within prescribed limits. For example, the first 6 terms of P100 are this. This is from the first 6 terms of his series. And you see it is already 0.64, 0.3, like that. So it is this. And he said, calculate nearest integer. Nearest integer is 292. And it is found that P100 is really this number, 292. Ramanujan was not happy with this approximate thing. He wanted to find an exact formula because the similar accuracy is there even for P200. But Ramanujan wanted an exact formula. But his earlier claim to an exact result for the number of primes up to n was proved to be wrong by Hardy. Because Ramanujan never bothered about proof. He said, what is the proof? This is the truth. Truth cannot be proved. Truth can be only realized. I've realized it, you take it. So Hardy proved that he was wrong. Intuition later obtained the exact result for PL. So at least in this case, maybe Ramanujan should have insisted a few more months. Ramanujan also provided a simple approximate formula for Pn as this. And is it how accurate? For n equal to 1000, this P1000, this formula overestimates the number by only 1.4%. Ramanujan could see, maths in the numbers. He also claimed that P5n plus 4 is 0 mod 5, that is divisible by 5. Partition of 7n plus 5 is divisible by 7. Partition number 11n plus 6 is divisible by 11. So looks like a formula is coming. prime number, 4, 5, 6. So P13N plus 7. Is it 0 mod 13? Unfortunately not. This is the formula which was obtained later, and Ramanujan stopped here. Not only that, he also claimed that P, if the square of these numbers are taken, 25, 49, 121, and 24, 47, 116, 1 less, 2 less, 5 less. This is 0 mod 5, 25, divisible by 25. This number is divisible by 49, and this number is divisible by 121. Somebody claimed that Ramanujan's most beautiful formula is this series, convergent series, and this continued fraction. Very simple looking. 1, 3, 1, 3, 5, 1, 3, 5, 7, all odd numbers. And here it is 1, 2, 3, 4, and this is 1. And he claimed this equal to root over pi e by 2. But neither this series nor this continued fraction has any relationship with these numbers pi and e. If somebody is interested, actually this can be done almost with school level algebra, but it is a little longer. So I can refer only to this Mathologer video. This video proves this formula. And this is Ramanujan's incredible continued fraction. He was the master of continued fraction, as I said. He wrote RQ as this. Q square, Q cube, and all. So if you put Q equal to 1, then it is that golden ratio root 5 minus 1 by 2. R1 is 5, root 5 minus 1 by 2. What Ramanujan said, that R of e to the power minus 2 pi, not 1, e to the power minus 2 pi is this. So through one formula, he is connecting e, pi, phi, maybe the most three well-known irrational numbers. Two transcendental and one just irrational. Ramanujan's creativity and magical ways of producing new mathematical results are sometimes attributed to his lack of formal mathematics education. He himself attributed it to the grace goddess, his family goddess Namagiri. But people say Indians are normally too religious to say such things. But actually, other great mathematicians from Europe, like Gauss, Pascal, Cantor, Littlewood, also believed that inspiration had a divine aspect. Even Gauss, considered as the greatest mathematician, said he once proved a theorem not by dint of painful effort, but so to speak, by the grace of God. Now comes the last commercial break. After the second commercial break, whatever I said is available in this book, The Story of Numbers, again written by me. So it is the commercial break. And now comes the most welcome slide. Thank you.